And welcome back to the channel. Today we're going to have a look at this altimeter. This is an old style steam gauge altimeter, but this one is very particular because it was built and it's meant for flight simulators, so it can be controlled by a digital interface. This particular one was installed in an old sim, dismissed one. I got a very good deal for it, so I decided to take it. And it's very well made. Everything is in metal. All this part here is in metal. This part here, which is which is the hose, was also it's also full metal one. I already, as you know, as you have seen, disassembled, by the way. And here is the interior. So we have here two potentiometers, these blue ones, and one DC motor. We also have a control board, which is this one which I already unscrew to make some to perform some tests. And in the back we have the two connectors, which are 25 pins connector. We have the first one, which is this one, and the second one. By the way, the first one is almost full, because I reverse engineered already the pinout, but the second one just has, the second connector just has 3 wires connected on it, and these three wires, one here, 2 and 3 there, 2 and 3 there, are this line here, which is connected directly to this potentiometer. This potentiometer in particular is for the baro setting here. And once again, I want to point out the build quality of this thing is very well made. You have all the gears, which are full metal gears. For the baro setting, also the knob is full metal one. Also the gears, the reduction gears for the needles are full metal. Everything here is metal. I think the only plastic, I'm not sure because I didn't check, but I believe that the only plastic things are the 3 needles here. Now I'm going to disconnect the main board, and I'm gonna show you how it works. So here is the PCB. We have the input connector, and then some ICs, in particular this one, this other one, and this third one. The first one is a digital to analog converter. This second one, this first one is an AD667. It's an analog converter, if I remember correctly, from analog devices, probably. Then we have this MUX, which is a 74S138, which is used as address selector for this PCB. We also have here a standard op-amp, which is used here as a comparator, a power amplifier, and then we have also the power section. So about the power section, we have in the input here something like a voltage which is between 20 and 24 volts. This voltage is regulated to actually, by the way, we have a plus and minus 20 volts or 24 volts coming here. The plus is regulated to 15 volts, plus 15 volts, thanks to the 7815, and the minus 20 or 24 volts is regulated to minus 15 volts, thanks to this 7915. The plus 15 volt also is regulated to 5.0 volts. This board I already changed something because I want to interface it later with an ESP32. So before here there was a 5 volts regulator. I already changed it with something with a similar pinout, which gives me 3.3 volts. In particular, I used this 29300 3.3 MT voltage regulator. Basically that's it. This is the board which actually drives the needles, and you have to know that the DC motor and the potentiometers are connected together. So this PCB here does something like kind of analog PID actually. How does it work? Basically, we have the digital signals 0 or 1, so basically from 0 to 3.3 volts in this case, because I changed this to 3.3 volts, so everything works with 3.3 volts. The 3.3 volts signals come here to this ADC, to this DAC, digital to analog converter. This is a 12-bit analog converter. So we have 12 bits coming inside here, but actually they used only 11. This PCB is then able to output analog signal, from 0 to 3.3 volts. The MUX here was used to select actually to activate this board. It was used with the A, B, and C lines of this chip, and as you can see here, you have several pins, and all these these pins are all of them connected to the activator, to the chip select of this ADC. So back in the days, this was a way to select this board with a particular combination, 7 bits of line A, B, and C, which come from here. It's not used anymore. Of course, I will not use this, and to have it permanently activated, I just retrieved plus 5 volts or 3.3 volts from this pin to this pin in order to have this PCB always active, because I don't need the selection anymore. We have then the comparator. This comparator here, this LM324, gets as input the analog signal coming from the ADC coming from the DAC, yes, which is a signal according to the bits, the 11 bits we sent here, and compares it with the voltage coming from the potentiometer. If the two are equal, the error will be 0. If the two are not equal, a signal is sent to this power op-amp, which drives the motor. We can briefly see the schematics on my iPad, and then we are going to see, we're going to try to make it work. Basically, I will give some 20 volts here, and I send some 3.3 volts to some of the ADC input, of the DAC input pins, and we should see the needles moving. So here we are on the iPad, and basically this is how the PCB works. So we have the input section. We have here the plus, probably plus 20 or 24 volts, the plus and minus, regulated to minus 15 and plus 15, and the plus 15 is also regulated to plus 5 volts, but in my case it's going to be 3.3 volts. And the rest is quite easy. We have the 12-bit lines coming here. So we have 12 lines that can be 0 or 1, 0 0.3.3 volts accordingly. They go inside the digital to analog converter, which gives output voltage here. At the same time, back in the days, it was used, the 74138 was used to select the pin, to activate, sorry, the digital to analog converter, but we don't need this. And then we have the op-amp, which is used as a comparator, which gets the voltage from the potentiometer, the voltage from the DAC, and tries to make both equals by sending an error signal to the power op-amp, and the power op-amp is going to move the DC motor, which is mechanically coupled to the potentiometer, in order to zero this voltage difference. That's all for this video. Bye.